Good morning. This is our 750 economic growth, and we are going to study poverty traps today. Let me share my screen. I have already some slides for that. Okay, so up to this point in the semester, we studied growth models. And obviously, these models are designed to explain growth, right? So in the models, we always have growing economies, right? But we also know that historically, today's developed economies spent hundreds of years, thousands of years in long-run stagnation. Okay, so compared to the 20th century or early 19th century, there was this poverty in all of these economies, and even today, some countries some countries fail to exhibit sustained growth in the long run. For instance, if you look at many countries in the sub-Saharan Africa, in the long run, their growth rates are near zero. Okay, so this is a challenge, right? So we want to explain poverty as well to understand growth and development in its entirety. Now, what is a poverty trap? So there is this nice definition by Azariadis and Stachursky. So they have this nice chapter in Handbook of Economic Growth. They define a poverty trap as any self-reinforcing mechanism which causes poverty to persist. Okay, so so we need initially an economy in poverty. Okay, and also what we need is some sort of a mechanism, some cause and effect system that causes poverty to persist. Okay, so there will be some structural elements that will make poverty to be the equilibrium state, for instance, for long years. Okay, so there is the authors also add, when considering a given quantitative model and its dynamic implications, the important question to address is how persistent are the self-reinforcing mechanisms which serve to lock in poverty over the time scales that matter when welfare is continued. So what does it mean? It means that long-run thing that we define, the time frame, must be, large enough, right? So we must be talking about maybe generations to compute the welfare and to compare welfare across generations to understand poverty. Okay, so time frame is important here. Now, typical example is this. This is, so there are many types of poverty trap, and there are many different mechanisms that explain persistent poverty. But the simplest explanation, the simplest model is this. So first, in some economies, suppose that there's low productivity of labor, right? And then output is just sufficient for subsistence consumption, right? So because the economy is low productivity, the output they have using the existing production technologies is small enough to make the output just sufficient for subsistence consumption. So what does this mean? This means they cannot save, right? People in this economy cannot save because they have low productivity, and they also have subsistence consumption constraints to be met. So they have no saving. But no saving means, if this is a autarkic economy, no saving means no investment, right? If this is a closed economy. And then no investment means no capital accumulation. Then without even knowledge, without even technology and without even endogenous productivity, if there's no capital accumulation, then productivity of labor will remain low. Okay, so since consumption, subsistence consumption constraints are still there in the next generation, the economy that uses the same amount of capital and the same technologies will still have low productivity, and low productivity again will create the conditions for existing poverty. Okay, so this is the simplest example possible, you know, from your undergrad lectures. Now the good thing is that we can actually formalize this idea, right? So this is the typical example modeled. Okay, so what you see here is a discrete time model. You are now familiar with such models. So there is this time frame, there is this utility function for people. The CT is consumption of the final goods, KT plus 1 is the capital stock left for future. Okay, and beta here is some, let's say, bequest parameter. All right, so the subsistence consumption constraint is here. Maybe I should use my stylus. Okay, so this is the subsistence constraint. So this is the utility function, right? So there is this bequest motive. This is the subsistence constraint. Okay, so gamma is a positive parameter. So consumption must have a minimum, right? And then the resource constraint is this, right? There is this production technology. You consume some of the production, and then you determine saving or investment. Okay. Now, important parameter here is eta. Now, eta is a parameter that may imply this situation optimal under certain conditions. Okay. Why is it there? Because as you see, look, utility is logarithmic, right? Now, without eta, imagine that what happens if eta is 0? When eta is 0, then an optimal solution requires this, right? An optimal solution requires this. When eta is greater than 0, this can be, that's important. I'm not saying it is optimal, but it can be optimal, right? From a technical point of view. So this is a trick we use a lot in the modeling of corner solutions, and in the literature there are some papers using it as well. Perhaps in a larger model with heterogeneous agents, some have eta equals 0, some have eta equal a positive number. But the end result here is that if that's the case, and if you solve this problem, what you will get is, I'm actually leaving that to you. So if you solve this problem, you're gonna realize, there is a solution to the capital accumulation problem, and this solution is piecewise. So it will be 0 if KT is greater than or equal to 0 then some level, and it will be some positive number otherwise. Okay, so what does it mean? It means if initial capital stock at time equals 0, if initial capital stock is sufficiently low than this threshold, let's say, okay, then KT plus 1, so then K1 will be equal to K0, okay? Then the same condition will be true for K1, okay? Implying that K2 is equal to K0 as well. Okay, so the poverty trap will persist. Okay, poverty will persist in this economy because people do not have sufficiently large capital stock so that their production, the largest production level they can have actually is only sufficient for their consumption. Okay, so that's up to you. So you should solve this model. Let me clear all this. So it's a very simple model. You just put it, put CT here, and notice that there's a constraint here. So there's a Lagrange function you can use. Now, what we're going to do today is to look at two models. Okay, both of these models are models of economic demography, right? So we are interested in the dynamics of population and especially the dynamics of fertility. In the first model, this is the typical Malthusian model. Possibly you are familiar with it. So that's a simple model, and in the long run of this model, because of land constraints and because fertility responds positively to income, we will have a long run poverty level. Okay, so the population and income will have fixed steady state levels, and that poverty trap, that long run poverty trap, will be a stable equilibrium. Okay, so in this economy there will be fluctuations. If we hit the economy with some shocks, there could be technology shocks or demography shocks. When we hit the Malthusian economy with some shocks, there will be some fluctuation. But once the shocks, once the effects of the shocks are diminished in time, the economy will converge to an equilibrium with constant living standards and constant population. Okay, and there's this recent line of research that shows for pre-modern economies, pre-industrial economies, Malthusian model actually has some important, has some good explanatory power. Okay, now the second model is like an extension of the first model, where these authors, Gary Becker, Kevin Murphy, and Robert Tamura, they introduce human capital into the story, right? So people now, again, trying to decide how many kids to have, but then they also care about these kids, these children's welfare. And welfare is carried on through human capital investments, right? So there's typically what we call quality quantity trade-off. So you are at some point, substituting better kids with more kids, right? So in certain cases, you may prefer to have 5 children and give them no education, or you may have 2 kids and send them to school. All right. So there is a trade-off between quality of kids and the quantity of them. Okay, so we're going to look at that model and why, under certain conditions in that model, we understand poverty is persistent. Okay, the Malthusian model. This is straight from Ashraf and Galor. I can send the paper to you as well. Maybe I can upload it. So very simple setup. First, there are 2 overlapping generations. Each adult have NT kids. Okay, so this reproduction event occurs at the beginning of the period. Okay, so that period, adults and children live together. At the end of that period, of course, adults die because this is a 2-period model, right? After the end of adulthood, adults die, and their kids who spent time T as children, they become adults of the next generation, right? So we have this equation that you see here, LT plus 1 equals NT LT. So there are LT adults. Each of them has NT kids. So NT times LT becomes LT plus 1 in the beginning of the next period, next generation. Okay, so that part is very simple. Now, endowments, that's also very simple. First, each adult has 1 unit of labor. Okay, so that's, you may imagine that this is time, and everybody works. So they supply this labor inelastically. They don't really care about leisure. And also, this economy has a total land endowment. Okay, because this is a Malthusian economy, and the Malthusian economy is dependence to land and natural resources is the key component. And so for this reason, we introduce land as an endowment. At the economy-wide level, it is equal to X, okay? And X is a constant, all right? So any positive number could represent the land endowment of the economy. Now, what are the preferences? Preferences are also very simple. So adults care about 2 things. First, they care about their consumption level, okay? That's CT. And they also care about their number of kids, okay? So as you see, there's no quality consideration in this model, okay? There's no education, there's no health. Only the numbers are important, and there are, of course, biological reasons for this. There are social reasons for this. So why to have kids? There are perhaps economic reasons, depending on the context you want to understand. But in economics, in economic demography, we most of the time assume that simple societies will have a utility function, and number of kids or fertility is usually modeled as a normal good. Okay, so as you see here, it's like any normal good, any normal consumption goods, so that you obtain utility from having kids, right? Maybe you like babies and the children, right? So that could be completely psychological as well. Now, production technology. Okay, so it's also very simple. This is a constant returns technology, as you see. X here is the land. AT here is productivity. This is an umbrella term for all the things that increase the technological sophistication of the economy. For instance, in this model, there's no physical capital, right? But if there is faster capital accumulation, you may imagine that AT is growing in time, okay? And LT is labor. Now, what is very important here is that the marginal productivity of labor, as you see, is decreasing in labor, right? So there is diminishing marginal returns with respect to labor. There's diminishing marginal returns with respect to land. So in total, at the aggregate level, we have constant returns to scale. Okay. And there's also the reproduction technology, right? So okay, the production technology tells you how to create goods, right? How to create consumption goods. The reproduction technology specifies how do you create kids, okay? And obviously there's a cost to it, right? And here in this simple model, cost is modeled in terms of the consumption goods, right? So if you want to bring one baby to this world, and if you want to raise him or her into adulthood, you have to feed these kids with consumption goods, okay? Here, that unit cost per child is rho. Okay, rho parameter determines the cost of one child. So, the idea we use a lot in this context is this: we define income simply as the average output, okay, or output per worker. Why? Because we don't want to deal with the land rents, right? So the problem that you solve is something like this. So there is this production technology, right? And suppose that you pay the wage. Okay, so if you solve this problem, obviously uh, there is positive profit, right? Because you don't pay here for the land. And suppose that this profit is IT. Now we assume that the profit is also distributed to workers. Okay. So instead of having this, then because of constant returns to scale, so this logic plus constant return to scale implies that income could be the average product. Okay, so that's the idea we use. What is the alternative? Well, the alternative is this. Let me change the color. The alternative is to define the land rent, right? So again, you have production, LT1 minus alpha. Now you pay the wage and you pay the land rent. Okay. Then in the economy, of course, you have to discriminate workers from landowners. Okay, because workers will obtain an income of WT and landowners will obtain land rents. Okay, but we don't want this to complicate our analysis. Why? Well, because it doesn't really change our. So it would be nice to have different levels of fertility for workers, okay, and different levels of fertility for landowners, and we will do that next week. But for now, to understand poverty, we don't really need that complication. For this reason, we completely assume away the land rents and distribute all the output to all the people that are working. Okay, so that's the idea. So let me clear all these things again. So at the end, what we have is this constraint, right? We already have the utility function. So you maximize this utility by choosing C and N under this constraint and under, of course, these constraints as well, right? These are non-negativity constraints. Then what you obtain is this, okay? So if you solve this problem, this is the consumption you have, and this is the fertility you have. So let's make sense of these solutions. Well, if you look at fertility first, it increases in gamma. Remember what gamma is. Gamma is the parameter that determines the relative weight of fertility. So obviously, if you really like kids, if the utility weight of fertility is larger, then you choose a larger level of fertility. Okay. Then, what's the effect of the cost? Of course, this is negative, right? Because if kids are becoming more costly, then you decrease the optimal level. And also, that's important, since kids are normal goods, and this is a typical consumer choice problem, obviously, higher income means higher consumption, right? So if you get richer, for some reason, you procreate more, okay? So that's the main Malthusian feature of this economy, right? Why? Because as Malthus said and argue very convincingly for his time, people procreate if they have more resources. They get married earlier if they have the economic means to support their lives and the family. Okay, so they in economic hardship, under times of economic hardship, under times of crisis, under times of economic contraction, people delay their marriage, people delay their fertility, and they look for a better time with employment opportunities and income opportunities, so that they get married at that time and they have kids at that time. Okay, so that is particularly relevant for, again, for pre-industrial societies. It is completely counterfactual for modern societies, and we're going to see why. But for now, if you are trying to understand, let's say, a feudal economy where dependence to land is a certain limitation, then that could be actually reasonable. And the consumption is determined by income only, and if you have higher income, you also consume more. Okay, and 1 minus gamma is your marginal propensity to consume, right? So that's all very simple. Now, of course, we are interested in the dynamic implications of this solution. Okay, so this is a unique solution, but we are interested in the dynamic implications of it. Why? Remember the earlier quote by Azariadis and Stachursky. We are interested in what happens in time when there is that self-reinforcing mechanism. Okay, and here is the result. So if you put NT back into the population growth equation, okay, and if you express this equation, right hand side of it, as a function of LT, what you see here is a strictly concave time, it's a strictly concave mapping from LT to LT plus 1, right? So adult population in generation T determines adult population in generation T plus 1, because fertility is endogenous now, and that relationship has a concave mapping. All right. Since it is strictly concave, if you look at this, you will see that it is strictly concave, right? You have gamma rho ATX alpha LT 1 minus alpha, and alpha is between 0 and 1. So it is strictly concave, and since it is strictly concave, it intersects with the 45-degree line only at this point, right? You are now familiar with it. Only at this point. And if there is an increase in productivity, if there is an increase in land endowment, then that curve would shift. Okay, as you see from this, because the same level of population in one generation would correspond a higher population level in the next generation. Okay, now you understand that there are two steady states. Of course, one is non-trivial, one is trivial, where population is 0, and the other is non-trivial when it is positive. Okay, now the dynamics, well, dynamics are very easy to understand. Let me use orange, let's say. So you start with some L0, right? You find L1 here, then L1 is also here, right? With L1, you find L2. So L2 is also here. With L2, you find L3, and it is here. And that goes on, so that you find this time path. So let me show you the time path in this color. As you see, the model monotonically converges to the steady state. Okay, you know that how it works. So in that transition, when population is converging to L star from a lower population level, we of course observe what? We of course observe, if AT and X are fixed, we of course observe WT decreasing, right? Because that's the idea. Remember, WT is equal to WT is equal to ATX divided by LT, right? So if LT is getting larger until it reaches the steady state, then WT is getting lower until it reaches the steady state. How do I know that this is true? Well, the steady state, if you solve it, features a particular level of income, right? So for this, of course, we assume this technology variable has some constant level in the long. Obviously, if you extend this model with continuous growth, okay, suppose that you extend this model with growth where G is positive, okay, then this cannot be a steady state. Why? Because A will be growing. Okay, so there's a different type of equilibrium you can find using balanced growth assumptions. Maybe I can show it to you. There's a nice paper by Lagerlöf, 2019, I believe. I also have a paper very recently published. So so this is, I guess, International Economic Review. And my paper is published in Economics Bulletin. Okay, so you can check these two papers to see how we can extend the multi-regime model with productivity growth. Let me now pause here. And if you have questions, I can answer them. Otherwise, after the break, we're going to continue. Okay, then. So let's take a break. It is now almost 9:50. So let's meet at 10:05. Okay.
Okay.
All right. 10:05. I will see you. Bye bye.